Okay, I think we nearly all of our audience has arrived. Our topic today is HDFS CSI and also how can we speed up the Kubernetes in on-premise environment. Of the big data clusters, first I want to introduce myself, and here is also my colleague Chen Yi. And she is the software engineer from Tencent and Apache Hadoop committer and PMC, and also working for a long time on the Apache Hadoop, HDFS and Ozone. And my name is Chen Junping, and I have done a lot on the massive data storage and computing. I'm the chair of Tencent Open Source Committee and also the Apache ASF member and also the Apache Hadoop committer and PMC. First, I want to talk about the big data and its history. Maybe you are the experts on Kubernetes, and I'm going to talk about the workload challenges on the big data and also different interface and solutions, and also some options for you to choose from. First is the history of big data. As you may know, it's first started from GFS of Google and Prometheus, and also started from 2003. And Abdul's establisher, the founder of it, has proposed the Hadoop project from its original project, and later is developed into the Apache Hadoop and also Hive as well, and he has built up the whole ecosystem of Hadoop. And in 2018 there were a lot of releases. Caldera company established, and about and a lot of the companies that is related to this field also established in 2012, 14, and 17 has pushed the development of big data into the 1.0 period, 2.0. In the 1.0, the foundation has been more mature, and 2.0, it has the scheduling and also the fetching of the abstract resources. After it has been splitted, it can be used on more complex big data calculation and computing as well. And also it's going to integrate with AI and deep learning. And the direction and chance in the future is utilizing the Spark technology. And in 2016, it started to come into being, and now has become a very popular engine for computing as well. One of the major events last year in the big data field is that two giants, Hotworth and Caldera, has built up the new Caldera, so it has entered the 3.0 era for its iteration. So this is the history of big data involvement. From the perspective of the big data stack, it has been separated into different levels. And that's how we have get mature big data. First is the NFS, and HDFS has become the foundation of all the big data. Of course, we utilize the others like S3 on the cloud and also on-prem. Maybe use Ceph, that is supporting the blocks and files, documentations, and different type of storage classes, and also the big data workload. On the other prospects, we also have other scenarios that have been supported, like supporting the ORC incubating and the MECC for its storage. And in the computing level, including its management and orchestration, it needs another resource negotiator. It's like the operation system of the big data systems. It's going to orchestrate those resources and also to manage some of the containers and abstractions of those containers. And it also tries to achieve the consistency of all of these systems. And then is the computing system, in computing layer, including the processing of the data and computing, and also the Hive engine, like the SQL and Engine and Spark as well. Just we also mentioned it's very popular, and also the mainstream technology, and it's utilizing Intel computing technology to support many different types of computing scenarios like machine learning and also some independent scenarios as well. And now there is another one is very popular. It's the real calculation, and it's very popular now. So all of these scenarios here will support different type of business scenarios of big data, including interactive querying, etc. There are different types of trends like streaming, and also the big data and traditional big data and its integration with deep learning. The strategic development of big data is like that. So how about the trends? First, it's going to migrate to the cloud. A lot of the big data workload has been migrated to the cloud and operated there. One of the core reasons is that the cloud computing is very important trend. Second is that the operations and maintenance of big data is very complicated. You can see the stack is very deep founded, and also usually it has a very big foundation. If you want to manage it, there is a lot of challenges on operation and management and maintenance. So it has to migrate it to the cloud, and also the integration with KBS, because a lot of the workload is transferring to the container. A lot of them are microservices, and before that, a lot of batch mode, and utilizing different waves of iterations to deal with their workload. In the future, if there is a whole set of the projects that utilize the microservice or the traditional ones, then it will increase the efficiency of the utilization of resources and integration of the clusters as well. And as for the layering of the big data system and its power, and I think the enhancement of these functions is that I know how can I scheduling my computing, and also so that my computing happened close to my data. And now I separated computing and storage. Computing could be elastic, but storage is very difficult to be elastic. So if we combine these two parts together, it will affect our business. How can we realize this elastic computing and separate this computing from the storage and also prepare for the replicas? I think there will be a very big room for us to innovate. Also, we are migrating to the cloud. There are some of the on-prem scenarios. We have a fixed clusters. If it has a peak times, we can flexibly expand it to do some deployment. This is another trend for it. And just now I mentioned containerization is very important direction. The benefits is very obvious. First of all, the hardware utilization will be higher compared with the VM. The hyper value can save a lot of the resources and reduce the consumption of resources as well. And also as for the split of resources or segregation, isolation of the resources, or from the perspective of security, it will be better compared with the traditional isolation from the perspective of network, namespace, CPU, GPU. It will have better state. And it also provided packaging solutions. So all the containers are able to seamlessly operate it on different nodes. You don't have to you don't have to care whether it's utilizing the native languages or not. And this is related to the independent states of different nodes. And here is the whole framework.
You can see that in the Kubernetes architecture, there's master, slave. On the master level, there's etcd, API server, and scheduler to control the resources. And also there are separation between different parts. And also the parts can talk to each other. So this is the overall architecture. Here are some challenges for big data. The first one is the orchestration and deployment. The optimized is using through microservices, and there are many big data workloads. It's around and around. So it's not you can finish finish it once and for all. It's a round by round distribution model. And second, the big data workload sometimes is using IOB. It's different from the traditional microservices, different manners. So the different types of workloads mix them together to distribute. The good thing is they can more efficiently integrate resources. The con is that if you can't segregate them properly, and SLA management to achieve the desirable level, it is a challenge or an important challenge for distribution and management. And thirdly, on the and for some scenario it's tuned, but for some on-prem environment it's not tuned. In some containers it used these ensemble storage, but they are temporary things, so I don't care too much whether they are boring or not. So overall, in terms of this sustainability, it's different from the traditional SBWH or other persistent storage. So this is some capability. So this is the background and challenges. Later on, my colleague Chen Yi will talk about CSI and other matters in design. Thank you. Overall, in-house and on-prem, using KPS to replace the traditional models, and big data storage is still using HDFS. So how can HDFS cope with big data workload while at the same time other workload on the platform? So regarding HDFS as a singular integrated storage, currently we provide the external storage interface at CSI. So I say a few words about the CSI. CSI, the whole name is a container storage interface. It's an identity service. And Docker Swarm, together with the industry, they jointly developed this interface. It includes on-spec, and the purpose is to bridge the container orchestration between different suppliers from different storage providers. And for providers, as long as they follow this spec, to make the CSI driver of their own, then it can be utilized by other providers. It's not unique to one platform. And the container orchestration provider, he only needs to provide this interface, CSI interface, so all the CSI storage can be used in this cluster. So it is an interface layer where different systems can interoperate, and it's not locked on one vendor nor one container orchestration provider. It's a neutral interface. And another feature of this spec, it pays attention to the control flow of the container orchestration, using the volume, managing the volume. And for IOF, the spec does not include IOF. The two designing criteria is to keep it interface as simple as possible, and second, the distribution, the using of the interface. Multiple distribution should provide yield the same result. CSI divides the service into three groups. Identity service. Identity service is used to expose the generic information about the driver, like the name, the version of the driver, and the capability of the driver. So this is a must service. And the second service is a controller service. And the main function of the first service is to cater to the user's demand to create and manage volumes. And the third service is node service. For some of the disks and cloud disks, this function enables the attachment or detachment with the VM. So this type of a service is we only need one instance, and that will be sufficient. And regarding node service, the main function is to, the volumes created by controller service based on the user's needs to mount it on the designated node. So it's a node-based service. In Kubernetes, on every node, we require an instance on every Kubernetes node. Besides the basic functions, the mounting and controlling, now the version 1.9, it supports many advanced functions. One is a broad volume. Back then, it's based on files, FS volume, and now it supports the creation of snapshot. So you can create a snapshot for a certain volume, and at a certain time slot, based on this snapshot, you can recover or restore the previous state. And thirdly, it's topology support. CSI supported these storages. Basically, they are mounted on their network-based volume. It's also distributed topology, so it's sensitive to the network. Under the same network, upon creation, this volume are only suitable for your Kubernetes, the nodes under the same network. And the nodes in some other networks might not be friendly to your applications or not compatible. So it's still optimized topology support. Before, the volume does not support besides. So the volume is immutable, and now it supports the resize of the volume. Currently, it only supports to expand the volume. Currently, and another feature is interim volume. Before, the volume's lifespan is not coupled with your system. If your volume still stands when the project's finished, you need to manually delete it. So it requires a manual deletion. And this type of volume, the lifespan will be the same with your pod. When your pod is released, then the pod will also release the volume as well. And the cycle of the volume, just now I said the lifespan of the volume involved the controller service and node service. And for controller service, it is responsible for creating and deleting the volume, while node service is will ensure that they are attached to the corresponding node, even multiple nodes. While creation, it only requires a very simple operation. So this is a CSI, two ways to deploy CSI services. Back before, I said your node service on each node, it's a must-have. And the difference between the two methods is whether you need one or multiple volume. One method is only need to deploy one, and it satisfies the above functions. And second one, if you combine the three services and deploy it on each node, it's also acceptable. But within the cluster, you only need one active controller service. If you deploy so many controller services on each node, you need a strategy to, to maintain only one active container at one given time, just like the leader of HDFS. You need to maintain one active service, and this deployment will be more intricate. So we would recommend the above deployment approach, so that you can maintain a simple architecture. Next, let's review in Kubernetes storage support the history. Earliest, all the Kubernetes supported storage, they are all maintained and developed by Kubernetes. The code were all owned by them. But with the popularization of Kubernetes, it needs to dock more and more providers and vendors. So it came to the epiphany that the model is not sustainable. So they shifted from the previous model to the outer tree model to dock the vendors. One way is called a flex volume, another is called a CSI. So far, Kubernetes no longer support. That means if you are just freshly docked to Kubernetes, it will no longer recommend you to using Kubernetes. It will instead recommend CSI. So for some of the intrigue rankings, Kubernetes is doing some work, selling some to outer tree and CSI model. So this is the future. Kubernetes will use CSI to dock third-party storage, so itself will not maintain the storage drivers. CSI driver spec is for the storage vendors, and storage vendors will follow the specs to deliver, to make their own systems. So how to acquire this spec, how to utilize this spec, actually there's still a gap in between. This is the driver's deployment. It's not a static process, it's a dynamic one. So that means how can Kubernetes dynamically identify that in this cluster currently there are how many CSI driver, because it's continuously changing, and how to identify how many existing storage drivers that are accessible, and how to develop the interfaces. So Kubernetes provide in the middle here, the green ones, it provides many auxiliary containers or components, but taking the form of containers. And these components, the functions, are assisting Kubernetes to identify that in this cluster there's some newly registered units, and on behalf and using Kubernetes code to distribute the interface of the driver, of CSI driver. Actually, the interface of CSI driver will not be directly used by the code, but through an intermediate, an ancillary component as agents. So, through these external components, these are auxiliary components, Kubernetes can dynamically identify the CPI drivers and leverage them, dynamically creating new drivers and corresponding to the volumes, all in a dynamic manner. Just like how Kubernetes support other functions, it's dynamic, no need for static configurations. So far, there are over 60 CSI drivers are supported. So in Kubernetes Hub, you can visit the booth to find out more. For CSI support, the history, let me add, it started from 199, and after a few versions, iteration, now it's a version 1.13, CSI part. The GA is 1.13, and it supports 1.0 as standard version. Speaking of CSI, I must mention within Kubernetes the volume support, the KPVB and Storage Class. And for PV, the perceived volume, it represents storage resources, and PVC are persistent volume claim. It's a user's demand, a description of a user's demand for the storage resources.
It's described in the port. When you describe the port, you need to also define the PV and PVC. They're sharing the same match. When the port is scheduled on the load, and it's going to generate a PVC if you need to store, it's going to find the corresponding system volume, consistent volume to satisfy your needs. For example, I need 100 gig. Then it's going to check whether they can find the consistent volume that can satisfy this demand. There are two ways. And for the bonding, it means that the resources need the admin to manually manage it, to establish manually. If there is no matching resources, it's going to process it in the other way. Another way is that we don't need the manual establishment of it. When we have this demand, if it is not satisfied, and it can dynamically create a consistent volume to it, and to build up the bonding relation between them. The key thing for the direct bonding is the storage path, storage class. It's related to the list of the storage. In its description, you may say that talk about what kind of things it needs. So everything is defined in the storage classes. Next is the suggested helper container, and it should help you to deploy, and also the way used to deploy. And on the left-hand side is the port. Is the suggested the node driver access register, and also deployed it as a daemon setter. So on each of the nodes, and the Kubernetes nodes will have this kind of node service instance. And on the right-hand side, it's a controller service and Kubernetes accessory containers, like attached container, provisional containers, etc., to build up into a pod and deployed as a sector. So this is a suggested deployment method. And our demand is that HDFS want to become an in-house clusters and provide the unified solutions for it. Then that will depend on the HDFS architecture. If you have listened to other speeches, maybe you have been quite familiar with this already, because HDFS has 3 replica by default for its data storage, so it's very reliable. And HDFS has about more than 10 years of experience and history. So it has the history of market deployment and operations and utilization. It has been a stable storage approach, and it's a very good candidate for Kubernetes storage. Now the default clusters number is very large, and also there are a lot of nodes as well. Single clusters may have more than 4,000 nodes, according to our understanding. But there are some federation cluster mechanisms. We know that there are more than 20,000, can easily get like several dozens of thousands of nodes. I also want to mention Apache Ozone. It's a very popular topic as a storage project in our ecosystem. And their developer are actually the developer of the Hadoop HDFS. So they have a lot of experience of different scenarios and operation and maintenance experience as well. Ozone is an object storage system. So its goal is to solve the scaling problem of HDFS so that it can achieve a cloud-native storage. This is the structure of it. If we want to put HDFS and Ozone as its persistent volume, is there any path? First is utilizing the HDFS NFS Gateway. The NFS Gateway is supporting that you are not belonging to the HDFS clusters, but maybe you want to utilize some of its nodes. Then on these nodes, you can deploy an NFS gateway and then put one of the root of HDFS to route to the local and take the NFS and take this as a local volume. And next is utilizing the root. So different storage will have different routes, and also it needs your deployment on different nodes because the gateway should be deployed on each of the nodes, and also should provide some daemon services to it, and a lot of configuring as well. So the process of configuration would be a little bit complicated. But now we have CSI, the auto identification mechanisms and mounting mechanisms. It will be much easier. So I think in Kubernetes, which is quite suitable, we can use the NFS gateway to develop a CSI and based on the NFS gateway, because Ozone supporting S3, so it can utilize its method to mount. So it can also, based on the S3 gateway, this is the utilization of Ozone on the Kubernetes. And it can also make it into a block device. We know that the NFS, the file system is very clear, but it's lacking a device like that. So they want to make a block device based on Ozone. And Cordra is also here. If you're interested in it, you can have a look. Well, so what is the benefits of utilizing this as the storage on it? Because it has 3 replicate, and also it's reliable during its existence, and it has very strong enforcement. Once you store this data, then you can ensure the consistency. It's impossible that you write it in this way and then its reading is different. And the speed of reading is very high. It also able to route different paths on your local. Of course, you can route different paths, so it's suitable for different users because they have different authentication. They may see different directory, so it's able to route different users to different place, and also to utilize multi-nodes mounting and read and write. The multi-nodes read and writes has one limit. You cannot writing the same file at the same time. It's not allowed. As for snapshot, you can do recite. Dynamic recite is not supported here because the snapshot is not supported here. And this is the deployment framework based on the NFS Gateway. Means you have to deploy NFS Gateway on the nodes, and also to utilize the CSI driver node, and then mount it on the local. And then it's able to provide the storage to you. And next is based on Ozone. Ozone is also recommended by many communities because it has object storage that can include the file storage. It's still developing its block storage. Next is some result. So time is limited. I'm not quite sure whether you have any questions. Please use the microphone. So its question is how to separate the workload on different scenarios. And usually it uses the I/O and also the bandwidth split or isolations. We have addressed it here. HDFS integrated and with Kubernetes into one product, and it's not trying to solve the native problems, but we haven't found the solutions on the cloud native. In the traditional fields, we have actually isolated different fields, and so that they are not going to influence each other. This is one of the reality. The NFS Gateway will support mounting one of them. So if you have several, then you need more. There is no limit. What I mean is that, for example, pod, maybe on one pod have one node may have 100 pods, different pods using different volumes, and of course on this pod we'll have different NFS. If it has several NFS, will it have any problems? For example, if you have 100 volume, we haven't produced it in a larger scale because for some of the applications, we are different to control which pod is utilizing which volumes in these occasions. What should we do? I think this is the practical usage. It's difficult to validate at the moment. I think the volume may be able to share between different pods. I think it's okay. Thank you. So this is the end of our speech. We can communicate.